Hi everyone. So today we're going to learn about centripetal acceleration. So, outline of what we're doing today. We're going to talk about what is circular motion. We'll talk about tangential velocity, and then we'll get into our main topic here of centripetal acceleration. I'll give you the formula and explain the formula for centripetal acceleration, and finally we'll look at an example of solving a centripetal acceleration problem. So circular motion, what is it? Well, as you guys know, we've been dealing mostly with linear motion, so movement along a straight path. Circular motion is the movement of an object about a single fixed axis. More simply, the object is moving in a circular path. Uniform circular motion is just circular motion, but the object that's moving in a circle is moving at a constant speed. So some common examples of circular motion are a Ferris wheel, a merry-go-round, a car making a turn, specifically a circular turn, and the goose in Duck, Duck, Goose, as long as the goose returns exactly back to the same spot that it started from. Tangential speed. This term is used to describe how fast an object is moving when it's moving in circular motion. We draw this tangential speed as a tangent to the circular path. And when it comes to speed versus velocity, remember that speed is a scalar, so it only tells us how fast the object is moving at that point in the circle. Velocity is a vector, so it'll tell us what the speed and in which direction this object is rotating in the circle. So velocity is very useful, and so is speed, depending on what you need to know. Here are some really nice GIFs about speed, or I guess in this case, tangential velocity. So the first image we have here on the left is of uniform circular motion. So this red arrow we have here drawn on this circle object moving in a circle. This arrow represents the tangential velocity. As you see, this arrow is drawn tangent to the path at which the object is moving in the circle. This vector does not change length, so remember we draw vectors as arrows. If the vector does not change length, it means that the vector has the same magnitude. In this case, because we're dealing with velocity, the magnitude of velocity is speed, so this object is moving at the same speed around the circle. And so this is uniform circular motion. On the other hand, we have an object here on the right that's in what's called non-uniform circular motion. So if we look at the velocity vector here, that is still tangent to our circle, the velocity vector starts out small and gets larger and larger. And as we see, if we just observe the object moving around the circle, it starts off slow and then gets faster and faster as the vector arrow indicates. And because it's a GIF, it automatically suddenly stops, where in real life it either slow down back to the original speed or keep going faster and faster. Now if an object is moving in a circular path, or even if it's just moving in just part of a circular arc, it has to have centripetal acceleration. If it's moving in any circular fashion at all, it has centripetal acceleration. That's really important to realize. So what does centripetal acceleration do? It causes rotation. It's also important to know that centripetal acceleration always points towards the center of the circle. Always. Always, always, always points to the center of the circle. Now, if the only acceleration acting on this object is centripetal acceleration, and this acceleration is at a constant value, so a constant acceleration, then this object is moving in uniform circular motion. In other words, centripetal acceleration only affects the rotation of the object, not its speed, not its tangential speed. So here on the right we have a nice GIF of an object moving in a circular path. As we see, we have the velocity vector, which is constant. Note that it doesn't change the length of the velocity vector, and it's also drawn tangent to our circular path. We have an acceleration vector that points to the center of the circle. The acceleration vector doesn't change length, so it's moving with a constant centripetal acceleration. And this acceleration is always pointing towards the center of the circle. Always. The formula for centripetal acceleration, there's actually many different formulas depending on what variables you use or how you're looking at solving the problem. The one that we're going to be dealing with in this lesson is the formula that relates centripetal acceleration to tangential velocity. So here we have an image of the formula, A sub c, so centripetal acceleration is equal to tangential velocity squared divided by the radius of the circular path. The units, so the SI units for centripetal acceleration are the same SI units for acceleration. Centripetal acceleration is just acceleration by another name. It's meters per second squared. Hopefully you remember that. If you don't, you could always use unit analysis. Remember that velocity is in meters per second. Radius is a distance, so that's in the meters. So you have meters squared per second squared divided by meters gives us meters per second squared. So dimensional analysis also tells us that our SI units are meters per second squared. This formula is really helpful, as you see by the relationship. If we increase the radius of the circle, think about what happens to our acceleration. As r gets really big, that causes our acceleration to get really small. If you look at the limit as r goes to infinity, so make r as the biggest number as you can think of, that means our velocity is divided by a super large number. That's going to cause our acceleration to get really small. Conversely, if we look at, let's say we stay at a constant radius, but our velocity is larger, increase our velocity, we'll see that our acceleration also increases. So if we have a large tangential velocity, we also have a large centripetal acceleration. Let's look at a quick example that I found just by a quick Google search. So here, example 3, even though this is our example 1, is the effect of radius on centripetal acceleration. So in this example, we have a bobsled track that contains 2 turns. One of these turns has a radius of 33 meters, and the second turn has a radius of 24 meters. So this is an example of having circular motion that's not necessarily the object's moving in a complete circle. It's just going in an arc of that circle, in this case in 2 spots. So we want to find the centripetal acceleration for each of these turns. So we're going to deal with 2 calculations here. And each of these turns, we're moving at a constant 34 meters per second. So we're in uniform circular motion. Our speed is constant. And then the problem here states we want to give our answer in multiples of g, where g is the acceleration due to gravity, 9.8 meters per second squared. Careful. G is not gravity. G is acceleration due to gravity. We'll be precise in our words. So let's look at our first circle here with our first turn here, the radius of 33 meters. We want to find our centripetal acceleration. Acceleration is our tangential velocity squared over r. Our velocity is 34 meters per second, so we square that, we divide that by our radius of 33 meters, and we get 35 meters per second squared. If we want to express this in multiples of our 9.8 meters per second squared, we take that 35 meters per second squared divided by the 9.8, and we get that this is 3.6 times g. So it's 3.6 g's colloquially, so 3.6 times the acceleration due to gravity that we feel here on Earth. When it comes to the second turn, we do the same math, except this time we deal with our smaller radius. So we have 34 meters per second squared divided by our 24 meters gives us 48 meters per second squared. This is a larger acceleration. larger acceleration of 4.9 g. If we do the math and convert to multiples of our 9.8 meters per second squared, and as we expected by looking at the formula, as we decreased our radius, we got a larger acceleration, and that's what we expect, right? We talked about that on the slide where we talked about the formula. So almost 5 times the gravity we feel on Earth, so quite a lot of g's. And the last thing I wanted to mention briefly is tangential acceleration. Tangential acceleration causes a change in the object's tangential speed. So if an object is speeding up as it's moving in a circle, this is not due to centripetal acceleration. Remember, centripetal acceleration just causes it to rotate in a circle. Tangential acceleration will cause it to change its speed when it's moving in the circle. So here in the GIF here to the right, the left GIF shows us our acceleration vectors. So just to mention, our red vector is acceleration vector, the green vector is velocity vector. So the GIF here on the left shows our tangential acceleration being, it looks pretty constant. It's a short arrow and it stays tangent and it stays that same length. Though if we look at our centripetal acceleration, the vector that's pointing towards the center of the path, it is increasing. The GIF here to the right shows our velocity vector. Our velocity vector is the green arrow. As we see, it starts from nothing because we start at rest and it increases in speed. So the velocity vector gets bigger. This makes sense. Acceleration is constant, which causes our velocity to increase over time. And the acceleration vector is actually our net vector, our resultant vector from adding these two acceleration vectors on the left, and they add to be the one on the right. Remember, we add our vectors tail to tip, or if you want, you can use the parallelogram method. But in either case, our net acceleration, so our total acceleration, doesn't point directly towards the center circle here because we have both centripetal acceleration and tangential acceleration. So that's all I have for you guys. See ya.